Any issues? Still working on it? Is anyone still stuck on this step? You guys all ready to go? Good? Are you good? 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 All right, cool, cool. All right. Where's my mouse? We're gonna scroll down to setup. So, not too much new stuff here. We're just gonna run them all down. Just make sure everything's working with Colab and your drive. So make sure you mount it on your drive. Um, this just helps show you what directory you're in. So make sure you wanna basically CD your way into the right directory where everything is. Here's again another look at your directory now. So you can see that we're going to be working with a Titanic dataset today. So the fact that you can see it all, that's good. And then finally, just we're going to import a couple different libraries. So pandas, NumPy, Matplotlib, and Seaborn. These are just common libraries we use with not only data pre-processing but also machine learning models, just making it easier to work with the data as well as visualize and graph it. So make sure that you download all those in, and then yeah, we're gonna take a quick look at the data set that we'll be working with today. So basically, we'll be working with the Titanic data set. So you can see right here, we get a little bit of glimpse of sort of the data we have. So we're given all this different information on our passengers, and we have to predict whether or not they survived or didn't survive. So we're going to be working with this data a little more as we keep going through. But before we move on, does anyone have any issue getting up to here? Really just been setup stuff, just making sure everything is good. Questions?
So, in the last workshop, you must have learned about data pre-processing, but just to give you a glimpse, data pre-processing is a very important step when you have large amounts of data. Um, you'll have some columns where you have NAs or NANs, and your model might not be able to parse that. We would not want. So generally, there are three things that you would want to do data processing. One is to remove columns and rows with a lot of missing values. A good example of this is, say you are parsing some genetic data which has very low negative values, and you write a code to have your model interpret NANs as zeros. Zeros and like ideally NANs would be depicting very low negative values like negative infinity, and you are writing a code for like your model to treat NANs as zeros, which would completely throw your model off track when you are testing it on new data. The second is no irrelevant columns like passenger ID, names, and tickets. Um, Generally, you can do dimensionality reduction for that. But you can also, if you are seeing like columns that have very little variations in them or have constant values, you can remove them. And then you can create dummy variables for categorical features like sets, like they have done here. If So here in the clean function, you are dropping kbin and you are dropping NANs in the next one. There's a code to remove irrelevant columns. And then here, if you see, you can see the text column split into female and male. This kind of splitting can be helpful in binary classification. Um, um, any questions regarding this part? You can go ahead and run the data pre-processing. Are you done with the steps? Yeah. Moving to train test splitting. So training and testing are the major components of a machine learning model. Generally, why do you want to test? Why do you want to test your model? Because you want to see how good your model is, right? But why do we want to split into training and testing data sets? Why don't we train on the whole data set and then test on some part of the data set? Because some models like decision trees have a have an ability to learn everything in the data that you are feeding it to be trained on. And if they learn everything, if the model memorizes everything that you are training on, and if you take a chunk of it, it will exactly predict the correct results, and you think your model is perfectly fine, it has 100% accuracy. But when you test it on new data, you see that your model is actually not that, like, not performing very well. So that is the reason why initially, before training, we would want to split the data into a training set and a testing set. So when we are testing the model, the testing set is a completely new data that the model has never seen. Um, Generally, you can keep the train to test splitting ratio as 80% to 20% or 70% to 30%, but frankly, it's on you. Um, Yeah, as noted here, one works as the learning material for us to train the model, and the other works as the final exam for us to test how good our model is after training. So generally, there are multiple methodologies in which you can test and validate your model. There's also a separate thing called validation of the model, not mentioned here, but it is an extra step to test your model, but I won't go into it. Um, you can go ahead and run the training and testing. Yeah. So if you see the set shape here, here the test size is 0.2. So your 20% data is the test data set. Since shuffle is true, it will shuffle the data set and pick 20% of the data randomly. And then 80% of your data is the training set. We can go ahead and run. Um, Generally, we use standard scaler because standard scaler normalizes the data. That is, standard scale the data such that the column has the mean of 0 and the variance of 1. We should not always blindly do standard scalar because sometimes you lose a lot of information in that. But generally, it's a good practice if your data is in the same range. It's a good practice to do. You can go ahead and run this. Do you have any questions regarding this?
So, so basically, we're gonna go into something called dimension reduction. So, just a quick question: why do you guys think dimension reduction is important? Before we really dive deep into it, ideas, thoughts. All right. So basically, dimensional reduction is pretty important because a lot of times you're going to get data sets with a lot of different features. Like we can see here, we have all these different columns. And if we want to visualize the space, that's going to be really tough because if we give each feature a different axis, you're going to get this huge, like, 8-axis hyperplane, and that's just not very helpful. So the idea is that we want to use PCA, which is a statistical method that helps project data in higher dimensions onto a 2D plane. Um, or a lower dimensional space so we can better visualize basically what we're working with and how we want to best train our models to fit our data. So because understanding how our data is sort of structured and related to each other will allow us to pick the best model for our purpose. So you can kind of see this is a nice little visual about how PCA is able to take this like multi their data and turn it just into an X and Y plane. So now we can visualize this pretty nicely and see sort of what we're going to be working with. So we're going to take a look. Here's another look at the Y train. And then we're going to look at this big chunk of code here. I'm going to zoom in a little bit. So sklearn is a really helpful library with a lot of different tools you'll be using as you start off your machine learning, journey. So you can sort of import PCA from here. And basically, for components, we want to tell the model, like the PCA, I'll call it a model, but we want to tell the PCA, okay, how many components do we want to break it down into? So we're going to say 2 components here. And then from here, we're going to fit the PCA onto our train data and then transform our data into these 2 different variables or data sets, so xtrain2D and xtest2D. And then from there, we're just going to plot it. This is just plotting syntax. I wouldn't worry too much about it. If you want to look at it on your own time, feel free. But we're going to take a look at the data here. So we can sort of see the blue dots are the zeros, or the people who didn't survive, and the orange dots are the ones who did survive. So now we took all these different features that were there before, condensed it onto this space, which is really helpful because you can see how the different people who survived and didn't survive are basically clustered or basically distributed across the plane. So based on this, like what you see from these graphs, what do you think is the best way to classify the training data? Does anyone have any ideas on how we could separate the orange from the blues? Thoughts? That's okay. Well, if no one really has any ideas, we're going to go into a different couple ways that we would tackle this issue. So basically, the task of classifying the training data, or basically splitting the zeros from the ones, that's going to bring us into basically the core of what machine learning is and why we need machine learning models. So.
What is a machine learning model? I think you all know that already because we have talked about. But a machine learning model, as we did here, is can be a mathematical representation of a real world process, but actually in computer science terms, it's a file or a program in which you can feed your data and it recognizes the pattern in your data. So if you basically feed some unknown data, it can correctly recognize what the data relates to. So there are multiple types of machine learning models. The 2 main types are classification versus regression and regression. Generally, classification algorithms are used to predict or classify discrete values such as male, female, true, false, spam, etc. And regression algorithms are used to predict continuous values. But this is not a hard classification again. You can see that there is logistic regression there because it is a type of binary classification. There are classification algorithms that can actually classify multiple classes. So this is really like just classification and regressions are like two broad classes in which you can broadly classify models. Logistic regression, decision tree. Decision tree is just a tree structure. If you have ever studied a tree structure, is like you ask a question. Basically, you want to determine if I can go out to play or not, and it depends on if it is going to rain today or not. So I'll ask the question: is it going to rain today? Yes and no. And then if it is going to rain today, then I'm not going out. But if it is not going to rain today, then will it be sunny? Yes, then I'm going out to play. So that is how your data is classified in a machine learning model. Then there's random forest, which is also a broader aspect of decision tree. There are support vector machines, and there is kernel SVM. So SVMs are of 2 types generally, linear and kernel. Both of them are classification algorithms. Linear SVMs are basically linearly can only classify data that is linearly separable, but kernel SVM can classify data that is not. non-linearly separable. Then there's k nearest neighbors. So basically, you randomly take points and find the k nearest neighbors around the points, and then optimize based on mean. And there's naive Bayes, which is based on theorem, which you probably have learned in probability. And there's neural. And for the regression algorithms, you can basically predict a continuous value, such as price, salary. Say, I input my age and and my degree, maybe my qualifications, and then I get a salary range. That is an example of regression algorithms. There's linear. There are multiple types of linear regression: simple, multiple, polynomial, support vector. You'll learn more about them in the upcoming survey of models.
Yeah, so after hearing about all of these, what kind of algorithms do you think we should use to predict if a person survived or not? So are we thinking classification or more regression kind of models? Classification? All right. Yeah, I would agree with that. We're going to take a look at a couple of these models now. The first one we're going to go into are decision trees or random. So, like mentioned before, decision tree is basically based off like a tree-like model that optimizes probable outcomes based off existing statistics. So that was pretty confusing, but basically, again, like you're gonna go to a node to ask a question, and from there, it's gonna basically move in whatever way best fits the data that was provided. We're gonna take a more clearer look at that in a minute. But before that, I want to go into a little bit about the Gini impurity. I guess you can call it a statistic or a number. So it's basically what this is a probability of incorrectly labeling something and helps us determine which node would be most suitable. So the idea is that a set that has one class of points has a really high purity and the Gini number is small. So I'm talking like you have 10 points and all of them belong to the same set. Like all 10 of these people survived or all 10 of these people did not survive. That would have a really high purity and a really low Gini number. Versus if a set has equal data from both classes, so let's say we have 5 survived, 5 not survived, your purity would be really low and your Gini number is high. So in the decision tree, we want to minimize the Gini number. So basically, we want to end up with a set that has all of one class of points. So think of it like at the very end of our decision tree, one side should have all survived, another side should have, or not one side, but like that group should have all people who survived, and another group should have all people who didn't survive. That sort of makes sense? Cool. So we're going to go a little bit into the math about how to calculate it. So it's very, very probabilistic, based on probability. So you can look at the math there. I'm not going to go too much into it, but sort of based on the probability of yes, this is going to happen, no, it's not going to happen. And then, yeah, we're going to go through an example really quickly. I'm just going to go through it really quickly because most of these are numbers, and it's more important that you just understand what they are. But we're basically saying that, let's say we made a model that only looked at what your gender was and used that to determine whether or not you survived or not. So out of the 259 women that are in our data set, 195 survived and 64 died. And then for men, 453 out of those, 93 survived, 360 died. So based off the formula over here, the one in the bold, kind of just simplifies everything. We can take a look at the sort of the numbers calculated here. So we can see for woman passenger we got 0.372, and male passenger we get 0.326. So we can just see we took like, no, they died, so the rate of that, so 64 divided by 259 here, 195 divided by 259, et cetera, et cetera. And then, so we can see that we got our values, but we're not done yet because there were less women in the data set than there are men. So we want the 0.372 to basically scale to that and weight to that properly. So we're going to take one last step here to calculate our Gini numbers. Oops, I didn't mean to do that. And we're going to get them right here. So you can see we just scaled them based off how many women or men were in the data set. And then we can see that there was a 0.135 chance, or the Gini number was a 0.135. There was a 0.135 chance of misclassifying a female. So saying like a female died when a female should have survived. and there's a 0.207 chance of misclassifying a male. So same thing, but with the males. So basically, we're going to take the Ginny numbers one step further. Basically, this is going to play a role in our nodes and our tree data structure because we want to basically say, like, a similar idea with the female-male thing here, but we're going to do this with every single feature going down. And we're going to use this to help basically split our data into basically whether or not they survived or didn't survive. So let's take a look at what this hidden cell is. So we're going to take the Ginny numbers one step further and take a look at their role basically in decision trees. So we're going to go into this, basically this little piece of code here. So again, import tree from sklearn. You're going to notice that most of your things that you're importing from sklearn sort of follow a similar pattern in terms of like how we train and make the model. So we're going to basically instantiate the model here. So make a decision tree classifier. Maximum leaf nodes of 8. So basically at the very bottom, you can only have 8 leaf nodes. Want to fit it to our data, right? If we were actually trying to make a model, we would actually want to use the common decoder over here. So again, like what we mentioned before with the train test split, if we just fit the model on all of our data, then it's going to learn exactly what was in the data. So you have really no way to test how well it actually is performing. So it's like if you were to take a test and I gave you the answer key to the test, I don't really know how much you actually know. So that way, if you actually want to train this data, this decision tree, you would use your training data here and then test it with your testing data later. But for now, what I really want to take a look at is basically this tree structure. So you can sort of see how, like, from the top it splits off and then downwards. So if we just start from the top and sort of take a look at a couple of nodes, we can sort of see that the first condition we considered was basically their gender. So genders we basically in our data set, in order to give it a numerical representation, we use zeros and ones. So basically say like, okay, if the gender is less than 0.5, it's one gender, greater than 0.5 is another gender. And you can sort of see the number of samples. So the starting number is 712, and it has a Ginny score of 0.482. And basically whether or not they're male or female is going to split off again. So let's take a look at the left side. Here we're sorting based off passenger class. And again, it's going to split off again and again and continue going down. So let's take a look at a couple of the leaf nodes. So we can see right here. This leaf node right here has a Ginny's impurity score of literally 0, meaning that out of the 15 samples that made it to that node, they were all within the same class. So let's say all 15 of those survived. That way you know that this portion of the tree is pretty good because you know that if there's an individual that makes it down to this leaf node, there's a really, really high chance that this person survived or didn't survive, whatever those 15 people are. Well, if we take a look at something like right here, a Ginny score of like 0.5, out of the 79 samples, it was like a 50-50 chance whether or not they survived or not. Since out of the 79, 35 did, 44 didn't. So we know that if an individual got here, it's still sort of like a coin toss on whether or not. That's sort of the logic behind why we want to minimize the Ginny impurity scores and how we construct our trees from that. I know that was a lot being thrown at you. Does anyone have any questions on decision trees before we sort of move on? Okay. So we're going to move on next to, there we go, logistic regression.
Let's first recap. So what a linear regression model does is if you have your data scattered, say on a plot, and then it tends to find a linear line of best fit. Okay, I think I should not go there. So when you're using linear regression, it basically makes this inherent assumption that your data is linearly separable. That is, a line can separate two classes on your data. A linear regression is a type of regression, so the output is a continuous variable, but the logistic regression follows the same concept except it uses discrete values. That is, you get a binary classification using logistic regression. So here, I think the example is really good that linear regression would be using height to predict weight, and logistic regression would be using height to predict whether or not someone is above 150 pounds based on their height. Here you can go ahead and run this particular code. Here we have imported logistic regression and then made a log model, which is a logistic regression model. We have fit the data and then predicted based on the logistic regression. If you want to try linear regression, you can simply change logistic to linear here, and then you can also change it here, and then you can run, and then you will be able to see results for linear regression once you are done. And then um, let me know what difference you see in both of them. And then here are the predictions. But at least for now, if you want to um, run this chunk of data, go ahead and run it.
All right. Everyone good with the logistic regression? All right. Cool. I'm just gonna keep moving through just because honestly don't know how long my computer's gonna survive. But so we're gonna move on to something called neural networks. So I'm sure a lot of you guys have heard a lot about neural networks. It's sort of like what everyone's talking about now. But basically, at a very basic level, neural networks are a collection of nodes that have basic connections to other nodes, and then these nodes basically make layers. So the idea is that you want to pass in your data to like the first layer. It's going to do some calculation on them, and then pass all that data onto like layers and layers after. Those own layers are going to do their own calculations and continue pushing it through until the very end, where it pushes out a result. So basically, neural networks are sort of are really good because it can learn a lot of different functions and super complicated models due to the large number of nodes, connections, and operations being done. So it's super interconnected and super cool. If you guys are more interested in learning more about it, you can click on the link here. So it's sort of a cool little playground that, ooh, okay, it's gonna barely load. So you can sort of play around with the different things here on seeing like how the different models can be created and the complexity with neural networks. And so increasing hidden layers will just make it more and more complex. So that's something to play around with. I won't spend too much time on that now. But anyway, so from sklearn, there's this cool little thing called MLP classifier, which is basically multi-layer perception classifier. So this is just your basic neural network with multiple layers, perceptrons or neurons, and then you're gonna basically instantiate the same way, but you have some extra different parameters here. So, for example, you have solver, which is basically like it's almost like the optimization function. You can take a look at sort of like the different options you have. If you take a look at the sklearn, what's it called? sklearn documentation. You can take a look at everything there. It's super well written, and you can dive more into the different sort of like parameters you can use. Alpha, that's your learning rate. So the idea behind a neural network is that you're going to calculate your way through, and then it's going to take the results and then compare them to what they actually should be. And based on that, it's going to back propagate through all the layers again. And it's going to basically update and it's going to update the different numbers and parameters within the nodes. So it basically like makes small alterations to the calculations that are being done at each step. So alpha is basically determines how much we want these things to change every time. So like we want them to change fast enough where we're seeing progress, but also slow enough where we're not missing missing a set of parameters that would be optimal. Like we don't just want to skip over it. Hidden layer sizes. So you can see how we have two hidden layers here. One with 3 neurons, one with 5 neurons. And random state, that's just an instantiation thing. Don't worry too much about that. So again, we're going to fit and train here. And we can sort of see right here that we have a training accuracy of 0.84, testing accuracy of 0.79. So this is something you typically see, that your testing accuracy is going to be a little lower than your training accuracy, just because it's new data that they've never seen before, so it's going to perform a little worse on them. But so far, it looks like our MLP classifier did pretty well. So I know I was really brief with what neural networks were, but do you guys have any questions on basically what I said? If you guys want to talk more about it, feel free to come up after, I guess, our little session, and I can talk to you a little more about it. I don't want my computer dying on you guys. All right. So one quick question before we move on to the SVMs. Um, so here we use three hidden layers, and then each layer with three neurons. Oh, okay. If we add more hidden layers or more neurons, will the model become more simpler or more complicated? What do you guys think? Right. So adding more layers and more neurons is definitely gonna make your neural network more complicated. But adding more is not always the solution because you're gonna run into an issue called overtraining, where basically you're taking your model and you're like overtraining it to the specific training set. So when you throw something new at it, it doesn't know how to handle it. It does really well in the training set, but anything new is gonna throw it off immediately. So that's why more is better, but it's not always better. If that makes sense. All right, we're gonna keep moving through to SVMs. Battery life. Ooh, okay. We're cutting it close.
So for support, we have two types of SVM, linear and kernel SVM. As we discussed above, linear SVM classifies a linear boundary, so this only works is linearly separable, and kernel SVM also classify a non-linear data set. So when the decision boundary between two classes is non-linear, that is when kernel SVM. Here, one very important part for linear SVM is that a linear SVM classifier has a linear decision margin if classes are linearly separable. Here, if you see the three decisions, um, what do you think would be the resultant decision boundary, which is the best for this data? Out of the red, blue, and green. So also like linearly classifies the blue and the green lines. If there was a line that was parallel to the red line, but near one of the classes, we still choose the red line because we want the margin to be maximum, and then this will be the line. And a kernel SVM uses a nonlinear function, which is called the kernel function, to find a nonlinear decision boundary with the maximum margin. Like how we discussed the maximum margin in the previous one here. Um, since the two classes white and black are not linearly separable, a curved line or a polynomial or a function to differentiate between the two classes. Again, it will choose the maximum margin. So if it has like if there is another line in question which is closer to the dot, it would still go with the red line because we want the margins to be maximum. Um, okay, which model will perform better on our data set? We are seeing the scatter plot for our data. What do you think? Um, which model will perform better on this one? I have a comparison coming towards the end. This is at least what type of SVM would work better for this? ESVM would work for this one. But out of kernel and linear, it would be kernel because our data is not linearly separable. So here again, for the code chunk, feel free to run by line of this, but yeah, from here we again use sklearn. Sklearn is probably one of the easiest libraries starting machine learning, and then we are importing SVC. Here, if you see, we mentioned the kernel as linear. There are multiple types of kernel. There's Here we mentioned RPF, which is a Laplace RPF. There is a Gaussian kernel if you want to use that. There are multiple types of kernel, which will be the function that you would use to differentiate two classes in your data. Here you can see testing accuracy and training accuracy. But I think this is, if you see these in linear, you see that the training accuracy is 0.77 and the testing accuracy is 0.79. Why do you think that is the case? There can be multiple reasons for that. I think the most obvious reason is overfitting. And the second reason is that most of your test data is easily classifiable. So for some reason, it was an imbalanced data set, and your test data was picked in such a way that it was very easily classifiable. It was probably just one label. But there can be multiple reasons for that. The most common one is overfitting. This is the kernel RPF, which is the kernel function. So here we definitely have a better training accuracy than the testing accuracy, and in general, mostly the kernel SVM would perform better than the linear SVM. But the linear SVM is lightweight, so when your classes are easily separable, you don't want kernel SVM. But feel free to try different types of kernel. You can go to the documentation for SVM and check out different types of kernels and use them, and you can just change RPF and then and see if you get better accuracy. Yeah.
Okay, so we sort of took a look at a couple different machine learning models, but now we want to take a look at how they did. So we're going to do a little bit of visualizations. So sort of some code from matplotlib, but I'm more concerned with this. So basically what these different graphs are showing are basically the data. So like the scatter plot we saw above, but also the boundaries that our different classifiers use to basically determine whether or not what to classify these as. So we can see here with the decision tree, we see a very like, oh, it's gone. We see a very like hard cut boundaries, so like almost like making right angles. So this is due to the fact that like decision trees, yes or no, split, yes or no, split. It's very black or white, 0 or 1, which is why we get this very hard edge right angle cutoff. And we can sort of see that like it sort of accounts for a lot of the orange ones here and a lot of the blue ones here, which is good. Logistic regressions, it almost looks like a linear regression right here, but this is mainly because logistic regression works. So that's why we get that sharp divide. And since there's only one sharp upwards in a logistic regression function, that's why we only get like one separation. What we get for that one. And then here we can see a neural network. So compared to the decision tree, you can see how neural networks are able to create a much more complex decision boundary. So you can see how they're able to sort of make jagged edges, cut around here, cut around here. So this is sort of the reason why not decision trees. Neural networks are sort of becoming more and more popular because they're able to create these complex boundaries that many other models cannot. So yeah, that's sort of pretty cool to take a look at. SVM, so linear SVM, pretty similar to logistic. It just creates a linear line through. Not much to it. And then finally, kernel SVM. So kind of similar to neural network, but kernel SVMs are sort of made in a way that they can create curves curved edges, whereas like neural networks can't. So like, well, they can, but you're gonna need a lot more neurons to do it. So like here, neural networks they can create these jagged edges, but they're still edges because you're going from one neuron to another. Versus in a kernel SVM, it's sort of built for you to create curved polynomials like this. You can get that nice curve around, and it also looks like it performed pretty well. Yeah, so pretty interesting to look at. Also helps give you a better understanding of the different models that you're working with. So whether or not to use a decision tree, neural network, kernel SVM, et cetera, et cetera. So I'm just gonna keep going through because we still got a little bit to go. Oh boy. Okay. I'm gonna go through this evaluation first. So basically, so after we've trained our machine learning model, we need a way to sort of see how they did. Yes, thank you. You have the HDMI. Yeah, right. That's fine. So we want to see how well they did. So here are some different metrics. So for regression, you have stuff like mean squared error, R squared. For classification, you have accuracy, precision, recall. And so one note is that you want to keep in mind sort of what your data set is. So if you have a really imbalanced data set, accuracy is not normally a good metric because the classes are not equally represented. So like let's say you had 99 people who survived, one person who didn't survive, and your model were to just predict that everyone survived, right? Technically, the accuracy would be 99%, but out of like all the people who didn't survive, you predicted 0% correctly, which is also not good. So you want to sort of keep in mind what your data set is, and from there pick the best, I guess, performance metric. So let's go through this really quickly.
So, as data sets have 90% of results and just 10% ones. So basically, 90% of your data set is like has person has a true result, and say you are making tests, and you get there is a very good chance that you get say you are picking 10% test split. So you have 10 samples in your test, and you have 9 from here and 1 from here. And even if you just predict all of them to be zeros, you still have a 90% accuracy. So whenever we have our data, it is always good to plot and see what the class is like. For imbalanced data sets, we have multiple techniques like mode analysis that you can use. Um, like SMOTE is synthetic minority oversampling technique, which is I think the most common technique used.